All right, so we're going to record a session. So those of you all who miss out the questions or don't see the tutorial, you can go through it again. If you're getting any issues, especially with tutorials, you can just look back at the video, go through your notes and see if you all can get them on your own. Remember, again, I will help you all out, but you have to start doing them on your own also. So let's hit the share speak. Good morning. Whose mic is on? Brandon, your mic is on. Thank you. So let's go to our handout. We have our handout here. Let me just get this one so I can see who's coming in. All right, so we have questions. I hope everyone can see these clearly. I did kind of increase it a wee bit so that we can view it. Ooh, okay. So let's just get some space. Good. So let's read our questions and see how we are going. Question 1. A sample of a certain nuclide which has a half-life of 1500 years has an activity of 32,000 counts per hour at the present time. Activity, remember, that's how much active nuclei are breaking down. Active nuclei are ones that are decaying by radioactive processes. So here we have 32 counts in an hour. When it starts to break down, that amount of counts is going to break down because we have less and less active nuclei present. So we want to first do plot a graph of the activity of the sample over a period in which it would reduce to 1/16 of its present value. So what you're going to do, plot a graph, meaning you all can just draw a really simple graph. If you want to go and do it on graph paper, y'all, I will never say no to using graph paper. I like to use graphs, as if you all didn't know that already. All right, so plot your x-axis, plot your y-axis, and we're going to do some estimations here. Now, if you all go and plot your graph yourselves, I would advise that you do that, so that way you can see it and try it on your own. Don't just watch what I have here as entertainment and then go your way. Don't do that. All right, you're not doing yourself any services by doing that, any favors. So let's start this up. We want to go to 1/16 of its original value. So you're going to go really, if we start with 3,200, 32,000, it's going to take a half-life of 15,000 years. So that means when it is, what is half of 32,000, y'all? All right, half of 32,000 is 1,600. So after 1,500 years, right, it is now going to reach an activity of 16,000. That is half of the original value. After another 1,500 years, it's going to reach to half of 16,000, which will be 8,000. After 1,500 years again, it's going to reach to half of that, which will be 4,000. Where are we reach right now? 1/2, quarter, 1/8. After another 1,500 years, we're going to reach to half of 4,000. Remember, half-life is the time it takes to decrease by half of that value. It's not just half of the original value, it's half of any value is your half-life. So what's half of 4,000? It's going to be 2,000, and you find your plot. And let's see, how do we know that this is, oh, somebody's joining room. So how do we know that this is actually 1/16 of our value? Let's check and see. Half of 32,000 is 16,000. Half of 16,000 is, wow, why did it do that? Hold on. Half of 16,000 is 8,000, so half is a quarter. You all understood what I did there, right? Half of a half. Then half of 8,000 is 4,000. So half of a quarter is 1/8. And then half of 4,000 is 2,000, and half of 1/8 is 1/16. So if you were to do this, I'm not even going to try to draw this curve right now. Well, I could. All right, I tried my best. All right, draw a nice clean curve. No, wow, that's a horrible curve. All right, a nice clean curve through as many points as possible. Remember, you do not have to get an exact curve. But in this process, since we're doing it backwards, where we're getting the exact half, you should get a really nice exact curve, and you draw your curve nicely. Remember, I taught you all how to draw your curves. You don't draw your curve going down like this. You turn your book upside down, and you draw it to follow the direction of your natural motion of your joint in your hand. So if the sample of the nuclide could be left for 2,000 years, what would the activity be? So what they want you to go, now this is where if you plotted a graph, you could go and read this value. They want to know what is the activity at 2,000 years. So you go in your graph. All right, now please note here, I was just checking every 1,500 years, but do we plot graphs by putting the same amount of numbers, or do we get larger and larger and larger?
Larger.
Larger and larger. All right, so after 1,500, what would we have?
Oh, I could put 2,000 if you're going in every 500.
No, well, here, this was 3,000, this is 4,500. All right, now, if I was plotting this graph, this is where you say, you want to plot your graph. I would have done 1,000 values. So that way I would have fit in the graph. So I would have done, if I was personally, if I was plotting this graph, I would have plotted 1,000, 2,000, 3,000, 4,000, 5,000, so forth. All right, so 2,000 will be somewhere around here. So all you're going to do, please go and plot your graph. All right, so get a graph page so you can actually read out your actual value. And you read up to where you are actually hitting the curve. Folks, I have seen some nonsense where people go, and if this is the curve, they go and read a value somewhere out in space. Don't do that. When we say we want a value from the curve or from the straight line, I want you to actually go and meet the straight line. Right? Or meet the curve. Get a point exactly on the curve itself. And if you read across there, if we were to read this, plot your graph and tell me what you get. All right, because this is again a sketch graph, not an exact graph, so I won't get my proper numbers. So if I was going up here, personally, if I were you all, I would have gone up by about 5,000. Yeah, I would have gone up by 5,000 every 2 centimeters for here. All right, so my y-axis would have been 2 cm to 5,000 for my y, and for my x-axis, I would have used 2 cm for 1,000 for my x. Personally, that is what I would have done, and I would have gotten a nice graph that stretches most of your page, and it's easy to take your readings. All right, so you all go ahead and give that a try again. Remember, I'm going to put up the questions, well, the solution collection. Those of you all who want to do it, don't want to do it, whoever's submitting questions and answers to me, I will correct them. All right, so question 2. The graph below shows the activity of radioactive sample of polonium-218-84. Well, actually, it's not supposed to be 84, it's supposed to be 84? Yeah, 218-84. So I have here polonium. In this case, I use mass. Mass and activity is basically how much I have, because when your polonium starts to break down, it's going to turn into something else. So you're left with just a certain amount of polonium. So you get the same thing here. Rather than use activity, they're using mass. Very rarely in exams will you see mass, but yeah. Here our time is measured in minutes. Right? Our activity is given in mass, but again, when a radioactive sample breaks down, it's going to break down and the other atoms are going to turn into something else. So here I have polonium 218, 84. They're asking what do the numbers 218 and what does the number 84 represent? Anybody? Anyone? You can answer by voice or by chat if you're feeling shy. You pull up the chat so I can see. All right, chat is up. What does 218 represent, folks? Or what does 84?
Number and the atomic number.
Okay, so 84 tells,
is the atomic number.
right? And what particle does 84 tell us about? '84 will tell us how many of what things are in the atom. Thank you. Protons, very good. Protons will be your atomic number, right? Where you are in the periodic table strictly depends on how many protons and or electrons you have. And 218, which is your nuclear number, represents how many of what particles? I will leave you to look that up.
Almost the number of protons and neutrons is equal to the mass number.
Number of protons and neutrons, right? Or the number of major particles in your nucleus. So if 84 is the number of protons and 218 is the number of protons plus your neutrons, you are able to determine how many neutrons you have. I'm not going to go through that. You're all going to work that out on your own. What is meant by half-life of a substance? We just did that. Use the graph below to determine the half-life of polonium-218. So what we're going to look at, all you have to do is just look at the time it takes to reduce from one sample number to half of that value. And usually, just as we did in class, you don't want to just take one. Take two and find an average. That's the best way to make sure that you're right. All right, so here we are starting with 50. What is half of 50? We're going to get 25 or about 25, close to 25. All right, and we can see that our first half-life, if you look at it, is the time taken to reduce by half. So you're going to get 5 minutes is your half-life. And if we want, we could take another value, all right, and see how much it'll take to decrease the half of that. What is half of 25? 25 is 12.5. So 12.5 will be somewhere around here. And you reduce it and you're going to read it down and see that 12.5, the amount of time it takes to go from 25 to half of its original value would be time it taken from 10 minutes to 5 minutes. And you're also going to get 5 minutes. Remember, when you're doing this, please don't make this mistake. And you all did this in class. And I wanted to beat somebody because they clearly weren't listening. When you're reading half-life, you just can't come here and read the time it takes from the y-axis to where you're going. You have to take the time it takes from your initial point to your half point, right? And 12.5 is not half of 50, it's quarter of 50. Everybody okay with that, right? You can give a thumbs up, say
Yes,
yes.
miss.
All right, good. Be very careful. Half-life, if you want to take half-life anywhere in the graph, all right? So suppose I want to take my half-life, let's not use the pen, let's go and use some lines. Draw. All right, suppose I wanted to use from 30, all right? What you do, suppose I just want to use my time from 30. First thing we do, we find out where 30 is on the graph. All right, so that's going to be your first point. And you're going to find half of 30. Half of 30 is 15. All right, so any 15 we want. So we find 15, about here is 15. All right, and then we see where that coincides on the graph. And we read down. And that's going to give us what we want for our half-life if we were to take it at 30 to 15. So we're going to read the time it takes to go from these 2 points. Y'all, these are giveaway marks. You have to calculate nothing. You just have to read 2 points from the graph and subtract. So pretty, please don't give away giveaway marks. That's a gift. Don't give away gifts. That's been kind of, no. All right, so let's move on. Just so that's following me. Okay, all right, hold on. Yeah, we have a stop on the page. All right, there we are. The following symbols represent 5 nuclides. So I have 5 nuclides here, 58, 8, 58, 29A, 57, 27B, 59, 29C, 58, 30D, and 59, 30E. Now, I want you all, somebody to tell me what is an isotope. Anybody?
Isotopes are atoms of the same numbers which have the same atomic number but different mass numbers.
So what is the same? Which number is the same? The number at the top or the number at the bottom? We have 2 numbers.
Miss what? What is the same?
What is the same? The numbers at the top are the same or the numbers at the bottom are the same? On top, miss.
The numbers at the bottom.
Numbers at the bottom. Because let's go through this very simply again. When we have, pen, seriously, right? When we have our symbol, remember we have protons, not multiply, saying add. When we have protons plus neutrons at the top and protons at the bottom, an isotope is a number that is an element that has different amount of neutrons. Same amount of protons, but different number of neutrons. So that means that the number at the bottom here, which is your mass number, does not change. Anytime we know we're dealing with isotopes, that means that the number of neutrons is changing. So all we have to do is see, anytime we want to identify an isotope of an element, just look and see at your proton number and your neutron number. If your proton number remains constant and you one of the top is changing, you know you have an isotope. So looking at that, question part 1, 2 part 1, I want you to tell me which one of these elements, knowing that, let me just leave this back on the board here. P and P plus. Why do I keep putting X? P plus N. Which one of these are isotopes of each other? Is A an isotope of B? Is B an isotope of C? Is A an isotope of C? You all look at them and tell me which one is an isotope of each other.
A is an isotope of C.
A is an isotope of C. Very good. Anybody else?
E is an isotope of E.
Say that again. You're really
D is an isotope of E.
Yep. Or vice versa. E is an isotope of D or D is an isotope of E. Same thing. Because if you looked at them, you're going to realize that we have the same proton as a big marker. All right. I guess no marker. If you look here, 29, 29. So obviously A and C are isotopes of each other. And if you look here, let's get next color so you don't mix it up. Right? D30 and E30. So we have the same proton number, which means they lie in the exact same element, right? Because remember, proton number defines your element, and they have different number of neutrons. Look here, you're going to see different number of neutrons. Funny enough, look here. This is where students would get a little confused. They say, hey, look. Right? Look, A has 58 at the top here, and D has 58 at the top here. Obviously, they must be related. Nuh-uh. This simply means when we add our protons or neutrons, we get 58. We can get different numbers to add up to give you the same thing. 5 and 5 is 10. 4 and 6 is 10. 1 and 9 is 10. All right, so be very careful. You want to look at your proton number, which is the number at the bottom, to determine whether or not something is an isotope of each other. When we have the same amount of protons, we are the same element. When we have different number of neutrons, we have an isotope. So moving on, let's look at part 2. Anybody can remember what's the formula for an alpha particle? Anybody? I have two numbers usually written here. What are those two numbers?
Four and two.
4 and 2. Malika, I'm going to have you stop answering just now. Rest of the class, you all just did this topic. Come on, man, do better than that. 4 and 2. And we know when we did alpha decay, when something undergoes alpha decay, what happens? Our nuclear number decreases by 4 and our mass number decreases by 2. Because when something gives off an alpha particle, this is A and Z. When it gives off an alpha particle, which is 4 and 2, we're going to end up with a daughter nuclide of A minus 4 and Z minus 2. So taking that in consideration, I want you to look at A, B, C, D, E, and tell me which one of those is a result of alpha decay, meaning you started up with your parent atom, your parent nucleus, it got rid of an alpha particle, and now the daughter particle is left there with us. So which one here, which two nuclides have differences of 4 and 2? There's actually only one answer.
A and B.
A and B. If you look at A and B, very good. If you look at A and B, all right, let's get a tiny marker. A is 58 and B is 54. So that means there is a difference of 4. And then we have A is 29 and B is 27. So we have a difference of 2. So you can say alpha A 58, 29 give us B 54, 27 plus your alpha particle. Why is the pen doing that? Ever so often, the pen likes to join up the 4. All right, so scribble that on quick. Or you can just watch back the video. Now we have here which nuclide can be produced from which other by the emission of a beta particle. Now for beta particle, what happens here? If you go through for beta decay, if I have XA to the Z to give me a beta decay, our daughter nuclide or daughter particle will still be A, and we'll have Z plus 1 plus a beta particle of 0 minus 1. So how do we get the daughter particle of a nuclide that underwent beta decay or mass number increases by 1? Which one of those particles, the nuclear number remained the same, but the mass number increased by 1? Which pair? You all look at them and tell me.
C and E.
C? C and E. Yep. C and E did actually, if you look at C and E, let's clear this off. If you look at C and E, you're going to see that, yes, the nuclear number remain the same, but our number of protons change by 1, and this is how we are able to change the material. Anytime something undergoes beta decay, it changes into something else. All right, so we 59 remain the same, and your proton number went up by 1. So that would give you C and E. All right, E is the particle that was created after C underwent beta decay. Hope you're writing this down because, again, it's coming in the quiz. One nuclide, so part 4 reading question. One nuclide emits gamma rays. Is it possible to determine which one does this with the information above? There's either yes or no. Anybody? Is there any way we can determine if there was beta decay, gamma rays given off here? Well, okay, give me yes or no. Tick or X. There is no way to determine if gamma rays were given off by a chemical equation. Why? Because a gamma ray is a ray. It is not a particle. So your number of protons and your number of neutrons and your number of electrons remain the same. Remember, when we do chemical equations or chemical balancing equations, we are looking at the presence of protons, neutrons, and electrons. A gamma ray is not a particle. So there is no way we can know by looking at this equation unless they told us ourselves. So I hope you all scribble that down. Unless the equation says that gamma rays were given off, there is absolutely no way we can look at an equation and say, yes, that has gamma rays. No way, right? Because a gamma ray is not a particle, and chemical equations tells us about particles. All right, and part 5, you all can do this on your own. Which nuclide possesses the most neutrons? Neutrons, so all you have to do there is go and subtract the proton number from your mass number, from your nuclear number, and see which one has the most protons. You all can do that yourself. All right, which is the big number minus the small number. Moving on. Aha. A different question. The sun loses mass at a rate of 2 by 10 to the 19 kilograms per second. So that means every single second is losing 2 billion kilograms every single second. If the speed of light in a vacuum is 3 by 10 to the 8 meters per second, calculate the power output of the sun in kilowatts. Now, this is several questions together. Now, first things we have here, they're telling us the rate of mass. Anybody remember rate of change? What does rate of change mean again? Rate of change means what? Anybody y'all can remember? We did that whole of first term.
Time.
We mean to divide by time. So that means rate of mass, or mass at a rate of, they are telling us how much mass is being reduced in 1 second or during time. So this is kilograms, not kilograms, mass over time. Just follow me here. All right, and they are telling us it is 2 by 10 to the 9 kilograms per second. They are saying that the speed of light, which is a constant, you all should learn this by now, but don't worry, it's in the Rubik sheet. The Rubik sheet is, you know, at the start of your exam paper, you have a whole bunch of values. It's always written there, right? So don't worry too much about it. 3 by 10 to the 8. I want to work out power. Anybody can tell me what is the basic equation for power and energy? Anybody can remember? No. All right. Power is equal to energy over time. So if you look here, we're going to have mass over time, and then we have speed. So this is what we're doing. Energy is, when we're looking at things that are moving at the speed of light, we always use Einstein's equation of E is equal to mc squared. All right, so mc squared is the energy of the material coming out or traveling at the speed of light. You don't always use half mv squared. Why don't we use half mv squared? Because this is for slower particles. Anytime something is traveling basically at the speed of light, we have to use E is equal to mc squared. So the only time we're going to use this equation is in this topic of atomic physics. When we're looking at things traveling at the speed of light, we don't use half mv squared. We use E is equal to mc squared. So you're going to here go and work out your energy, which is mass, 2 by 10 to the 9, multiplied by 3 by 10 to the 8, all squared. And that's going to give me 2 by 3 is 6. 8 by 2 is 16, 16 plus 9, 10 to the 25. Anybody check that? Tell me if you get that. That's shortcut in maths if anybody don't know. Oh no, squared, sorry. 18. This is 18, 26. 1.6 by 10 to the 26. All right, so we're going to end up getting 1.8 by 10 to the 26 joules. Now, I want to determine power. I just worked out energy, but if you look here, they said that the rate of mass is 2 by 10 to the 9. So that means every single second, we have a mass of 2 by 10 to the 9 being given off. So we can always now say power is equal to energy over time. And since I already had the mass over time here being 1, I can say that my power is 1.8 by 10 to the 26 joules. Since I am using mass, rate of mass, and rate of mass is mass over time. And to get our power, we're just going to have the same equation. Now they're asking to work this out in kilowatts. How do we convert from joules, watts? How do we convert from watts to kilowatts? To convert from watts to kilowatts, all we're going to have to do is divide by 1,000. And when we're dividing by 1,000 using law of indices, oops, sorry. How can I get more space? No, not footer and header. All right. When we have to divide by 1,000 using law of indices, dividing means we're taking away. So we're going to end up getting, oh, why is my thing different? Okay. We're going to get 1.8 by 10 to the 23 kilowatts. This is a really mean question. Honestly, it is. I don't think you get it at this like this again. All right, but if you all see a simple question like this, rate of mass simply means we have the mass being divided by time, and that time can be translated to your next equation. Question 5, 3 nucleides X, Y, and Z have half-lives of 1 minute, 24 hours, and 10 years, respectively. I will have to send you a handout.
A question.
Yes.
Miss time here was 1.
Yeah, time here was 1 per second. So that means every single second it gave off 2 billion kilograms. So we make the assumption. So if it's saying per second, we can work out the power every second that's being generated by the sun. It's a little iffy question. I don't think you get things like this again in exams. All right, but if anybody is doing question, this would be from older papers, like from my years before 2000, you'll get questions like this. All right, so those of you all who are doing past papers, you end up seeing a rate of something, this is what you're going to end up using. You don't see it again like this, but just to give them a try, because I always say, let's do more work than too little. Let's learn harder than easier. So 3 nucleides, I will have to, remember I said I have to send you a handout on how to do this. I will, on how to use radioactive isotopes for medicine. That's in the handout that's coming. So you'll answer this from the handout, very, very simply. A radioactive sample is found to be emitting on average 880 particles per second. So that means every single second is giving off 880 particles. If the source has a half-life of 25 minutes, how much time will elapse before the average emission rate becomes 110 particles per second? Remember, particles per second tells us the tells us what the activity is, how it's behaving, and as time passes, your activity is going to drop because we have less and less particles to give off. So don't use the per second here as any sort of indication. It's just they're telling you basically how fast it's breaking, you know, how much is there. So if I had something that has a half-life of, it has 880 particles, and then I wanted, it says a half-life of 25 minutes. So that means after 25 minutes, it will reach 440. After another 25 minutes, so we can put 50, it will reach 220. After another 25 minutes, which is 75, it will reach half of 220, which is 10. So how much time will elapse before it reaches 110 particles per second? 25, 50, 75. So the answer here, it will take 75 minutes to reach to an activity of 110. Everybody okay with that? Yeah. All right. So really, you see how you all can just go and jot this down. Imagine if I wasn't talking. This literally took a few seconds to do. Literally took a few seconds to do. Because if I was just doing it, I would have done 880, 25. Guys, gals, this is how I would have done it. 50, 440. Oh no, 25. Yeah, 220, 50, 75, 110. That's how I would have done it, real fast, like 5 seconds. All right, so it's not something where you have to sit down and go and plot the graph. You don't need to go and do all of that. Explain why the measured count rate is unlikely to be 110. Why is it unlikely to be 110? Because half-life is a random disintegration. The disintegration of a radioactive nuclide is a random process. It's not something that happens exactly on the point. We use it as a guide, but to say it's going to reach exactly 110 after 75 seconds, right? Remember when we did the graph in school, y'all, that's how we did a best fit curve, because not all of the time we're going to get the same or the amount that we need to fit the graph perfectly. All right, so why is the count rate unlikely? Because radioactive decay is a random process. It does not happen exactly the same all the time. This gives us a really good count. It gives us a really good check, but it's not perfect because, again, it's a random process. What will be the effect on the count rate if, one, we gently heated the radioactive source, or we heated it to a very high temperature? Does anything affect how a radioactive sample breaks down? Yes or no? Anything? Does anything affect it? Can we do anything that changes how radioactivity behaves? There is nothing we can do that affects how radioactivity or how a nuclide breaks down. The only thing we can do is shield and protect ourselves. But to say we can do something that's going to stop those alpha, beta, and gamma particles and rays from coming out, there's absolutely nothing we can do. The only thing we can do is to put something around it so that we don't get exposed to it. But to say we can stop it or we can slow it down, absolutely nothing we can do. All right. Question 4, question 7 here is basically doing subtraction, addition, and subtraction and multiplication. Let's go through it real fast. I'm not going to work it out. All right. But let's follow up. When a C14 isotope decays by beta emission, it becomes an isotope of nitrogen. The mass of C14 nucleus is 2, that small number, and the mass of a nitrogen 14 nucleus is that next small number. Calculate the difference in mass of the nuclei C14 to N14. You're just subtracting the bigger number, the smaller number from the bigger number. You're not supposed to get a negative value. Take the big number minus the small number. All right, so just do your subtraction. Determine the energy released when one C14 nucleus decays. Again, when we're looking at things that travel at the speed of light, and how do we know we're going to be using Einstein's equation? You have to be traveling at the speed of light. Guess what's happening here? They're telling us that it's traveling at the speed of light. So we're going to use the equation of E is equal to mc squared. Do we have the mass? Yes. Do we have C? Right? So all you're going to do is just multiply mass by C squared, and you're going to get your value in joules. Right? Energy is always measured in joules, so please put them in joules. Right? I think a couple of you all, well, not the whole class is here. I don't know what the rest of the class is. Anybody in school today? I find the class really small today. Anyone?
I'm not sure.
Yeah, Miss Vanessa in school.
What do I have today in school? Tete-Tots?
No, I
Nutrition.
think she had to go for something for food and nutrition.
Food and nutrition, because I know their moderation is coming up, so that could probably be it. All right. So you just multiply the mass by the speed of light squared, and you get your answer. Please put your final answer 2 decimal places. All right, because here you see why we have to put all the decimals, because it's really, really, look at it. 3, 2, 4, 5. 3, 2, 4, 5. So it's just down to the last 2 decimals that are different. So that's why we have to really, really detailed and really, really accurate when we come to dealing with the atom, because it's so very teeny tiny. Okay, this is the one I wanted to show you all how to do, because here's the next question in the handout. So during a nuclear fission reaction, uranium isotope 23592 uranium absorbs a neutron and splits into barium and krypton and 3 neutrons, as we've done in the notes on the class last day, with the release of energy. This is represented in the equation below. So we have 235 absorbing a neutron. It breaks up into barium and krypton, and we get 3 excess neutrons going on to form our chain reaction. The table below gives the masses of the particles involved in this reaction. So we have neutron, uranium, barium, krypton, all its masses. Now you all know I have an issue with this table, right? I would have written down 10 to the minus 27. All right, this is how we would have done it in class, right? And then we would have just not had this in the table. Let's just make life nice and easy. All right, but then you all will make mistakes, as I have seen people making mistakes of forgetting these things. All right, make life nice and easy, because just see numbers in front of you. All right, what is the total mass of the uranium nucleus and the neutron? So I want to get what is the total mass of the uranium nucleus and the neutron. So y'all, again, this is just addition, simple addition. So I'm just adding a neutron plus to the uranium. That's question 1, part 1. What is the total mass of the 2 nuclei and 3 neutrons produced in a chain reaction? So my chain reaction was a barium plus a krypton plus 3 neutrons. So all you're going to be doing is adding barium and krypton plus 3 neutrons. Again, that's simple addition. All right, you're multiplying the neutron mass by 3 and you're adding it to the barium and krypton masses. How much energy is produced as a result of the fission reaction? So what you're going to be doing, how do we get this? We want to work out energy. Energy of your reaction would have been E is equal, why did my pen get so small? E is equal to mc squared, and the m here would be the mass of all my particles together. So it would have been the mass of part 2, which is the mass of all my nuclei and the 3 neutrons produced in the reaction. Because remember what happens here, when we are splitting uranium, we take uranium, we fire a neutron into it, it absorbs that neutron, it becomes unstable, and then it explodes to give us our barium, krypton, and 3 neutrons. So our energy as a result is going to be the reaction of, or the explosion of these 3, well, 5 things. So how do we get our energy? Using, again, they're telling us velocity, our speed, is 3 by 10 to the 8. So we know we are using Einstein's equation of E is equal to mc squared. So we're going to have E is equal to mc squared, where we use the mass of all our stuff after the explosion multiplied by the speed of light squared. See why we have to use a very small number to work this out? So you all have to be very, very, very careful when you're doing the multiplication and using your standard form. Be very careful with it. They were doing this calculation before they invented calculators. So you know you have to do this by hand, right? Imagine trying doing these calculations by hand. I can't imagine doing it. I would love to do it because I like doing crazy things like that. But that's wow. They did these things by hand, not a calculator, by hand and with sliding rulers, which I don't know how to use. All right, so you all can give that a try. It's going to take a little too long to work out right now, but we're going to put it up in the classroom. So question 9 shows how to do radioactive decay sequence. You're all just going to see which part has alpha and which part has beta. We already did a question just like that. So you're going to see which one of them changes by 4, 2, and which one of them changes by 0 minus, well, you're adding 1 to the number, right? By 0 and plus 1. And question 10 is almost exactly like, I know it's written as 6, it's just a picture of an old question. It's exactly like question 8, right? Here, what we're doing instead, let me just zoom in here. Remember they said to go and use atomic mass, unified atomic mass. Remember I had given you a table. They said that the unified atomic mass is used to represent a small number. So each U represents 1.66 by 10 to the minus 27. So if I wanted to go and work on my questions, I here have big pen. All right, 233.03964. If you want to convert this to kilograms, you're going to multiply the 233 by 1.6 by 10 to the minus 27. All right, so use that. Now, if I were you, I would just use these numbers, add them up, and then multiply them by U, because 2 by U plus 3 by U is not the same thing as saying 2 plus 3 multiplied by U. Anybody? Is that the same thing?
Yes, miss.
Yeah, it's the same thing. All right, so this is why they've given us this little substitution to use, because I'm pretty sure it's easier to add these numbers than going and working out. Look at the value here. Let's just go back up, rather than using these long decimal points and whatnot. All right, so I've given you the 2 examples, the 2 ways of using this equation. All right, question 4. They've just asked you to work out the calculated amount of energy released in the fission of uranium-233. This is exactly like question 8 or whatever is above. All right, exactly the same thing. All right, so give it a try. All right, and you can work it out. If you want to go ahead and convert each U to kilograms, all right, all they have to do is do the 233.03964. The 0 is the point is here. Multiply by 1.66 by 10 to the minus 27. You multiply it through and you get your answer. You try to keep as many decimal points as possible because you need to be precise with this question. The only reason why we don't round up to 2 decimal places because the values are so very small. We need to take them in consideration. So 233.03944 by 1.66 to the minus 27. If I were you, I would try to keep as many decimal points as possible. All right, but look at the problem. If you all go ahead and convert this to kilograms right away in the question, if you convert this to kilograms right away, you're going to end up with a whole bunch of other decimal points, which just going to give you a headache. Oops, sorry. All right, you don't want to be going through all of this trouble. So what I would do if I were you, use your masses in terms of you first, right? Do your addition and subtraction using these values, and then when you finish doing the addition of your masses, then you go ahead and you multiply it by 1.66 by 10 to the minus 27. Pretty please. If you go ahead and convert each term, right, to kilograms first, you're going to get really long decimal numbers, and you're going to do strippiness. I would personally, I would do strippiness, and I would leave out something. Okay, and I'm pretty sure I can remember this number to work with for the whole question, but that's the next thing. All right, so we're going to wrap that up. And let's see what else we have to do. So we're going to wrap that up here. Stop share. Bring out screen here. So again, I'm going to post up these questions sometime, not today, probably tomorrow. All right. In the Google Classroom, where you're going to submit your answers. I'm going to see who gets what right. And then we'll go through, I'll put up the solutions in class. Well, probably solutions in the Google Classroom also. So you can compare them. I'll put up a solutions sheet so you can compare them to what you did. Please try them. Don't just say, you know what, I'll wait for Miss to give me the answers. You're not doing yourselves any services by doing that. Or, you know, any favors by just waiting for me to give you the answers, because in exams, you're on your own. So let's try them on our own. You've gotten the instruction. If you're getting any problems, go back and check the video or check back the working and see how you're going to get them. I think we're nearly finished. A few people still have work outstanding. For me, you have until the end of the day. If I do not get those outstanding submissions and outstanding labs, you are going to get 0. All right, I've given you far more extra time than you needed to. If I don't get them, I'm going to give you 0. Please send me pretty, very nice, crystal clear pictures of your work, and not pictures that are unreadable and completely illegible. All right, so folks, I will see you again on, when will I see you all again? On Friday. I will see you on Friday. So we are going to start thermal physics on Friday. So you all have a good week. Enjoy your week. It's hot. Drink some water. Drink lots of water. And if you have any questions, please make sure and send them to me. So have a good day. Bye-bye.
Bye, Miss.